So what we're going to talk about today, guys, is the force of gravity. Okay, we're going to talk about kind of how it works, but more importantly, how it's calculated and what kind of things can affect it, right? Because up until now, the way we've calculated the force of gravity is to go like this: Fg equals mass times the acceleration due to gravity, which is fine, provided you know what little g is. The problem is little g is different everywhere. We just approximate it to be 9.81 all the time. It isn't, right? Around here, it's actually more like 9.83. Right? We're actually closer to the center of the Earth here than you would be at sea level at the equator. Right? The Earth's not perfectly round. Right? So actually, it's widest at the equator. So you are actually lightest at the equator. Okay? You're actually heavier at the poles. Weird, but true. Okay? And we'll talk a little bit about that today as well. So little g changes. Okay? But the big thing here is we're going to be talking about gravitational forces between like Earth and the sun, okay, or Earth and the moon. Big, huge distances. Little g doesn't apply in that kind of a relationship, okay? The moon is not accelerating towards the Earth at 9.81 meters per second squared, thankfully. Okay, it is okay, a lot different, and we're looking for the force of gravity between them. Michael, you had a question. Absolutely. Yep. No, absolutely. And it would be, well, it would be pretty much across the board, like running or jumping, gravity would be affected. As an example, in 1968, the Olympics were held in Mexico City, which, I mean, it's not at the equator, it's closer, but it's also a very high altitude. And the long jump record was broken in those Olympics by a huge margin, and it wasn't broken again until the 90s. It was the long jump record stood for almost 30 years, okay, which is unheard of in Olympic sports. But every other Olympics was held in locations where gravity was higher, right? And they were more northerly areas, okay, where Mexico City was more equatorial, things like that. So it does make a difference. I mean, when we're able to measure, you know, to the thousandth of a second in events now, yeah, it can certainly make a measurable difference. Because I mean, we're talking the difference between, you know, at the equator, it could be like 9.78, right? Whereas here, it's 9.83, right? I mean, that's a pretty significant. I mean, it's 5%. It's what? Yeah, about 5%. Okay, so it's a big deal. Okay, and you know, if you're a well-tuned athlete and you're consistent, you're going to see an improvement just because you've changed location. Well, I mean, in any event, it's going to have the same effect, right? With the throwing events, you have air resistance playing a bigger part against the implement. So at in some places you could have, like at the equator, the air is typically more humid and heavier, right? So you have that offset as well. Okay, so we want to learn the relationship between the force of gravity, okay, mass and distance, okay, because we haven't really talked about how gravity works up until today, okay. What makes gravity? Okay, so space-time is like this sheet, and you can see the gravity wells in the sheet. That's a representation of what gravity would look like in a two-dimensional space. But why is there gravity? What makes gravity? Okay, that's where we imagine, yeah, the center of the Earth is where we imagine the Earth's gravity to originate. Okay, but why does the Earth have gravity? Actually, yeah, that's a common answer, but it's actually not true. The Earth would still have gravity even if it didn't spin. Not even because it orbits. You're making gravity right now. The bigger your mass, the more you can pull towards you. Okay? Mass is what causes gravity. Anything that has mass generates a gravitational field. The more mass you have, the more intense and the larger that gravitational field would be. The gravitational field of the sun extends out well into like beyond the Kuiper belt and into the Oort cloud, which is like this weird area beyond the Kuiper belt. Okay, because the Earth or the sun, sorry, has an incredible mass. Okay, the Earth has a a gravitational field that keeps the moon in orbit around it. Okay, and all satellites in orbit around the Earth. Why does that work? No one's really sure. There's a lot of research going into, what causes gravity? Is there a gravity particle? Like, is there a graviton? Okay, is gravity a wave? Things like that. What we know from a mechanics standpoint is gravity is a field force, and anything with mass can generate gravity. Okay, you and I can generate gravity. It's incredibly puny, and no one would ever notice it. Okay, like if you or I were out in deep space, we could not attract a mote of dust towards us by gravity. Okay, our gravitational field would be so small because we have so little mass. Okay, but something larger definitely could. Okay, and someone once asked me, so if I kept eating, would I get big enough that food would come to me? Theoretically, yes. Practically, no. Okay, because you would still be on Earth, and the Earth's gravity is always going to be larger than you. Okay, and so things are always going to be more attracted to the Earth. All right, that's why when we throw something up in the air and it falls, okay, it falls towards the Earth. It doesn't go, ooh, there's a person there, and like move towards us and then fall to the Earth. Okay, we're just puny. Okay, we can't generate any respectable or even measurable, really, amount of gravity that could cause any changes. Okay. All right, and obviously gravity can act as a centripetal force. If it didn't, things wouldn't orbit other things. Okay, the whole celestial mechanics thing would break down very quickly if gravity could not act as a centripetal force. All right, so force of gravitational attraction toward the Earth for a 70-kilogram physics student. All right, so if I am on the Earth's surface at sea level, I weigh 684.6 newtons. Okay. If I'm at sea level at the North Pole, I weigh 688.3 newtons. I'm heavier, 4 newtons heavier at the pole. Okay, I'm the same mass, but I'm heavier at the pole because the Earth is flat. Or yeah, I did not say the Earth. It is flatter at the pole than it is anywhere else. So the Earth is flattened. Okay, not flat. It is flattened. Okay, and most planets are actually visibly flattened. Okay, you can actually see that they're not perfect spheres, especially the faster they spin. Saturn is one, okay, where it's visibly flattened. It's much wider at the equator than it is at the poles, okay, and Earth is no exception. So we weigh more there. Okay, if I'm in Chicago, okay, so about 2/3 of the way from the equator to the pole, okay, I weigh 686.2 newtons. Again, heavier than I weigh at the equator. At the top of Mount Everest, the highest point I can stand on the planet, and I'm still heavier than I am at sea level at the equator. All right, so even though Mount Everest seems like really, really tall, in terms of affecting your distance from the center of the Earth, it's like minuscule. Okay, so the things that can affect how heavy you are, that is the gravitational attraction you feel. Okay, the things that can affect that are your mass, the mass of the Earth, and how far you are from the center of the Earth. Okay, those are the things that can affect the force of gravity that you feel. Probably not, because bone density can also have a big genetic factor. Yeah, so I would say probably, you probably wouldn't notice it because it's also very, very small. All right, so that's kind of different places on Earth. If I'm in low Earth orbit, where the International Space Station is, I still weigh 647 newtons. That probably seems weird because we saw Chris Hadfield doing all that zero gravity stuff. How could he do that if he still has weight? Yeah, it does. It has to do with the fact that he's orbiting. He's apparently weightless. He's not really weightless. Okay? He's really just, because he's going in an orbit around the Earth, it's like he's always going over the top of a vertical circle. Okay? And so he always feels apparently weightless. If he was weightless, he wouldn't orbit the Earth. It's his weight that keeps him in orbit around the Earth. If there wasn't any weight, he'd fly off. Okay? So he does have weight. It's just because he's moving in a circle, he looks weightless. All right? If I'm in high Earth orbit, that's quite a bit further away. Okay, in high Earth orbit, where like our geosynchronous satellites would be, okay, I would weigh 15.5 newtons. Why the big drop? Right? Like I go, all of these are fairly close together. Even low Earth orbit is still fairly close to these numbers, only 40 newtons difference. Why all of a sudden when I get out to here, does it drop so significantly? Well, we're imagining those other masses aren't there. You're right, there could be other masses that it could be attracted to, okay? But we're going to say that those aren't a factor. Yeah, you're getting closer. The further away you get, the less gravity affects you exponentially. Okay, so as radius from the center of the Earth increases, the weight that you feel decreases exponentially. Okay, so it's an inversely exponential relationship with distance. Right? If I was out at the same distance the moon is, I would have still some attraction to the Earth. Right? With my puny mass, it's not very much. Okay, with the moon's much greater mass, okay, there would be a much greater force of gravity holding the two together. Right? Which is why the moon doesn't just fly off. All right, everybody with me there? Is the moon's gravitational field pretty big? Yeah, how do we know that? Okay, I can walk on it. I weigh 1/6 what I would here when I walk on the moon, but I can walk on it. Tides. Yeah, we see the effect of the moon's gravitational field here on Earth. Okay, because the ocean is fluid, it actually moves towards the moon. Okay, because the moon's gravity is pulling it. All right. You see this actually in other places in the solar system. Okay, there are some moons that orbit the bigger planets, like Io, for example, the little volcanic moon that orbits Jupiter. Okay, it gets squeezed and stretched by Jupiter's gravity all the time. Okay, as it orbits, okay, it gets pulled by not only Jupiter but also all the other moons that orbit Jupiter. There's like 60 of them. Okay, but some of them pass fairly close, and so what's always happening is there's this constant pulling and stretching that happens on that little moon. Okay, making it like very unstable tectonically speaking. Okay, and so it's always got all these volcanoes and things like that erupting on its surface. Okay. We see that a similar effect, but not to the same extent, in that the oceans move towards the moon here. Okay. All right. So obviously we can see then that there's a fairly large, or that distance has a fairly large effect, okay, on the attraction that things feel. Okay. All right. So at this point, if you were in Mr. Dickey's class, he would do this activity that makes everyone feel incredibly awkward, but it's funny. He makes you look at the person next to you deeply into their eyes and say, I'm attracted to you. It's creepy, and it's true. Not in that like sociological sense, but in a gravitational sense, it is true. Okay, you do have some very small gravitational attraction to every single object everywhere, right? It's just so incredibly small that we can't like measure it. All right, now here's the big thing about gravity. We always envision gravity as the Earth pulling on us, but it's not. It's mutual. We pull on the Earth just as hard as the Earth pulls on us. It's a mutual attractive force between them. The only thing is that the Earth is so incredibly massive compared to us that it doesn't move. Okay, like there's no measurable change for the Earth. Okay, whereas for us, we would experience an acceleration of 9.81 meters per second squared towards it. Okay, but the any two masses will exert a mutual, and that is the key here, mutual attractive force upon each other. Okay, and that's why we see some places in the universe that there are actually stars that orbit each other. Okay? And actually, more recently, we've even discovered that the moon and the Earth orbit each other. The moon doesn't truly orbit the Earth. The Earth and the moon orbit a single central point that just happens to be inside of the Earth. Okay? Because the Earth is so much more massive than the moon, okay? That there's a common orbital center, okay, called the barycenter, okay, that is in actually just under the Earth's surface. So the Earth actually wobbles back and forth. Okay, as it orbits the sun, it actually wobbles back and forth because of the position of the moon. The moon pulls it away and towards and away and towards, okay, all the time as they go around. Yep. Yes, because they're very close in size. Yes, so Pluto and its largest moon, Charon, okay, have this same idea. Okay, Charon is the boatman that takes you across the river Styx. There's a naming system, by the way, to all of the moons and planets and stuff in the solar system. So Pluto is the god of the underworld, and Charon is the person who takes you there across the river. Yeah. So anyway, okay, but they are very close in size. Okay, very, very close in size, and so as a result, you can actually see them orbiting a common center. Okay, it looks like initially like Charon orbits Pluto, but they're actually orbiting a central point. Okay, together. Right, and that's true for most things. I have no idea. Disney does a lot of weird things. Yes. Yes. Disney does a lot of weird things, like kill Luke Skywalker. Who knows? Like, come on. Yeah. Okay. So, so when Newton studied these attractive forces, okay, because Newton was kind of the first person to get this idea of gravity, right? There's that story about how he was sitting under an apple tree contemplating all of this stuff, and an apple fell and hit him on the head, which is a total lie. Okay, that didn't actually happen. He just used it as a story to explain that the Earth and the apple were equally attracted to each other, and he got in the way. Okay, that was the whole idea of the apple hitting him on the head thing. Okay, so what he discovered was that yes, two objects, any two objects, can exert a mutual attractive force on each other. Okay, he had this idea. Okay, he knew that it would work. He could observe that it occurred, but he couldn't mathematically make it work. Because what was always interfering? If he wanted to do an experiment on two objects and their gravitational attraction to each other, what would always interfere? Well, not so much him, but what's the biggest thing around us? Yeah, the Earth's gravity. Okay? The Earth's gravity always messed up his experiments because you go, okay, ready, go, and they would fall. Right? They just fall to the floor and like, well, that didn't work. Okay? It was really hard to measure the gravitational attractive force between any two objects within the Earth's gravitational field because the Earth's gravitational field messed it up all the time. Okay? And it was big and strong, and there was no way he could negate it that he could think of. All right. Now, someone came along later and designed an experiment that did just that. Okay. But he never was able to make it work because he was always missing this part of that formula. Okay. That formula you see there is the Universal Gravitational Law. Okay. It applies, as far as we know, everywhere within our known universe. Okay? It is Newton's Universal Law of Gravitation. Oddly enough, he's given credit for it, even though he never made it work. Okay? And what it says is the mutual attractive force of gravity between object 1 and object 2 is based on the masses involved and their separation distance. That is the distance between their centers. Okay? And it is key here to know that this is separation of centers. I always spell separate wrong. I'm not going to spell separate. I'm going to spell distance. And then I don't look as foolish. Okay, distance between centers. Okay, so R is the distance between the two centers. And that becomes important when we start dealing with like celestial distances, right? If I'm standing on, let's say, the surface of the moon, okay, I need to know the radius of the moon because that's going to be the distance I am from its center. Okay, or if I've got a satellite orbiting the Earth, I don't want to know how far above the Earth's surface it is. I want to know how far from the Earth's center it is. Okay, we're always worried about the distance from the center of something to the center of something else. Okay, so Newton realized this part of the equation. He knew it worked. He knew it was true. Okay, he just couldn't ever make this number come out right. Okay, he couldn't make it come out to what a scale would say. All right, so he was missing big G. Big G is the gravitational constant of our universe. Okay, it was calculated by a guy named Cavendish. Okay, and its value is 6.67 times 10 to the minus 11. Okay, and it is, hang on here, GR So that's Newton meters per kilogram squared. Yeah, Newton meters per kilogram squared. That's its units. Weird, but that's its units. Okay, so it is, okay, like we say, it's the number that makes this formula work out right and actually give you numbers that aren't ridiculously large, right? Because when Newton was trying to make this work, he was finding that the gravitational attractive force between the apple and the earth was enough to crush the earth. Okay, and that's obviously not possible. So he was missing something, right? He was missing this number. All right. As we can see in that formula as well, okay, r is squared. So as we said before, separation distance has an inversely exponential relationship on the force of gravity. The farther away I get, I will be exponentially less attracted to whatever object I'm moving away from. So absence does not make the heart grow fonder. Distance does not make things stronger. Sorry, I'm anthropomorphizing. Okay, it's not. Yeah, it is gravitational attraction, and in fact, all field forces, magnetism, electricity, they all decrease exponentially with distance between. Magnetism and electricity are really strong over incredibly small distances. Gravity is the only force that can exert like measurable and actually incredible forces over huge distances. Okay? When it comes down to it, like per kilogram, gravity is the weakest of the forces. But because it's always dealing with so much of the stuff that generates it, mass, okay, its force is the one that we see versus, we're dealing with 2 electrons. Well, big deal, right? There's not a lot of force there because, well, they're 2 electrons, right? Okay, is this making sense so far? This idea of gravity. Okay, so we'll talk a little bit here about Cavendish's experiment here. Okay, so Cavendish developed. It didn't look exactly like this because Cavendish was around before lasers, but he used a beam of light. Okay, from like through a slit. So he developed this, which is called a torsion balance. Okay, and as we said, Newton couldn't run any experiments because every time he tried to run a gravity experiment, Earth's gravity would be the only thing he could measure. So what Cavendish did is he set up an apparatus like this that was perpendicular to Earth's gravity. Earth's gravity would not have any effect on the attractive force between the objects. So we had these 2 big lead spheres that were on this rod together, okay? And it was placed so that it couldn't move. Right. Then he had this essentially like a piece of wire, light wire, and he knew the strength of it, and he knew how many newtons it would take to twist it X number of degrees. Okay, he knew its torsional strength. Right. So what he did is he took 2 small like pith spheres, like really lightweight stuff, okay, almost like ping pong balls, they'd be something like that, okay, and he attached them to this torsion fiber, which had a mirror placed on it. When he set this apparatus up, the pith ball and the lead sphere were attracted to each other gravitationally, and what resulted was that the fiber twisted. Earth's gravity wasn't causing that to twist. The only force that could be causing this fiber here to twist would be the gravitational attraction between these masses. Okay, so he now had mass 1 and mass 2. He knew how far apart they were, so he had R. He could use this to measure the force of gravity because he knew it took X number of newtons to twist this a certain number of degrees. So he could just measure how many degrees his light was deflected from straight on. Okay, since he could calculate the force of gravity, then he knew, okay, M1, M2, and R. He could isolate for the number Newton could never find, big G. All right, being able to calculate that number allowed us to do all kinds of calculations for like celestial objects. Without this experiment, we would have never launched anything into orbit. Okay, we would have never gone to the moon, which we did. Okay, it's not fake. All right, we would have never sent probes to other planets or anything like that. Without this formula, none of that stuff would have worked. Okay, this formula here allowed us to get the number we needed to calculate gravitational attraction. Okay, everybody kind of follow Cavendish's experiment here. Okay, Cavendish, that was a pretty important experiment. It made Newton's universal law of gravitation work. It should really be Cavendish's universal law of gravitation because he's the one who made it work, but Newton gets credit for everything. Okay. And then this graph here, guys, okay, this is an inversely exponential relationship. All right, we're seeing that the force of gravity, which is here on the y-axis, is decreasing on an exponential curve with distance. So when I am like 2 Earth radii away, okay, I'm feeling this much gravitational force. When I'm 4 Earth radii away, okay, it's 1/4 of that. Right, it's 0.5. Right? It's inversely exponential. I only got twice as far away, but the gravitational force between was 1/4. Okay. Questions there? So here's your first example problem to do with Newton's Universal Law of Gravitation. Okay, a melon is taken to the moon as a food item by astronauts. Okay, we know Chris Hadfield said that they occasionally get shipments of fresh fruit, right? While the MythBusters were there eating those nice-looking apples and tormenting him. All right, so they take it to the moon. Its mass is 0.65 kilograms. All right, so there's one of our masses. Okay, we'll make the melon mass 1, 0.65 kilograms. The mass of the moon will make mass 2, and it's 7.36 times 10 to the 22 kilograms. Considerably larger. Okay, and the radius of the moon is 1.74 times 10 to the 6 meters. Since the melon is right on its surface, that's going to be our what? It's going to be our radius. Okay, so if I want to calculate the weight of this thing, okay, I could go Fg equals m times g, but I don't know what g is on the moon. It's not 9.81. Okay, so I can't use this formula. But what I can use is this one, because this works anywhere. All right, so if I'm going to calculate the weight of the melon on the moon, I'm going to take the universal gravitational constant, so 6.67 times 10 to the minus 11, multiply that by the mass of the melon, 0.65 kilograms, and multiply that by the mass of the moon, 7.36 times 10 to the 22 kilograms. And then I'm going to divide that by the radius of the moon squared. What do you suppose the most common mistake is when using this formula? Forgetting to square radius. Should it be pretty obvious if you forget to square the radius? Yes, because you will get an answer that is exponentially too large. All right. So if I'm asking you, like, calculate the weight of something when it's 1 kilometer above the Earth's surface, you should probably get a number pretty close to its actual weight. But if you forget to square your answer, you're going to get an answer that says it's gigantic and it's like the moon pulling on the Earth. Okay. Should you recognize that right away? Okay? Those are things you want to be watchful for, because I see people make mistakes like that, like on an exam, and they leave an answer that makes no sense whatsoever given the context of the question, just because they plugged it in and said they were done, rather than looking at their answer and going, well, that answer doesn't make much sense. Okay, make sure you always look at your answer to see if it makes sense. Okay, so when we plug these numbers in, there's a lot of typing to do here, guys. So I would caution against trying to do it all in one step. Okay, because if you try and do it all in one step and make one mistake, you're doing it all over again. Okay, so I kind of do it one piece at a time. All right, so I'm going to have the, first off, I'm going to have the universal gravitational constant, 6.67 times 10 to the minus 11. All right, and I'm going to multiply that by the mass of the melon, 0.65. And then I'm going to multiply that by 7.36 times 10 to the 22, mass of the moon. All right, so there, I've got the top done. Okay, I know all the stuff I typed in there was correct. Now I'm going to divide by the bottom. All right, so that's going to be 1.74 times 10 to the 6. All right, and then square that. Brackets are important here. Whoop, that's not squared. Stupid. Okay, 1.74 E6. Okay, the squared needs to go outside the brackets. Otherwise, where does it think you want squared? if you put the square right beside the 6? Okay. I'd be cautious about that because I've seen it not work a lot of times. Okay, so please be careful in entering. Okay. All right. So we get that the weight of that melon on the moon is 1.05 newtons, whereas on Earth, it would weigh almost 6 times as much. All right. Okay, so the Earth, the moon's gravity is 1/6, okay, of what Earth's gravity is. All right, questions on how that one worked there? So when we're manipulating, is that going to be terribly difficult? Okay, just moving stuff around, right? It's all multiplication and division, so you don't have to worry. All right, the other thing about gravity, obviously it can act as a centripetal force. Right? It can keep things in at least somewhat circular orbits. Right? If there was no gravity, then things would obey Newton's first law, and they would travel in a straight line at a constant velocity. Right? So what happens to produce an orbit is something has this tendency, its inertia, to go in a straight line. But gravity pulls it back towards the center of the object. But it wants to travel in a straight line. But gravity pulls it back towards the center of the object. But it wants to go in a straight line. I'm not going to do that all the way around. Okay, get the idea. Okay, if I connect all these points, right, it produces a circle. An orbit is the product of an object's inertia and acceleration due to gravity. As long as you're moving fast enough, you can orbit something. If you're not moving fast enough, gravity is the bigger part of this equation, and instead of being a circle, it becomes a spiral. Okay? And eventually, you encounter the object in question. Theoretically. Okay, so the question was, if I could go to the center of the Earth, would I be weightless there? Theoretically, yes. Practically, you'd be burnt to a crisp. Yeah, and crushed on top of that all. Yeah, because the Earth has a solid or semi-solid molten iron core kind of thing, right? So there'll be a lot of pressure in that area. Okay, is that making sense there? Okay, so orbits are caused by the combination of inertia and gravitational attraction. All right, so like we said, if there was no gravity, it would just go in a straight line. Okay, and that's what we just talked about there. Okay, so circular motion under gravity, okay, is the basis for all satellite motion, okay, which we'll talk about later on in the week probably. Okay, but this is how we calculate all satellite motion. Fc equals Fg. Gravity is providing the centripetal force for any object orbiting another. Okay? As a result, we can calculate how fast objects are moving in their orbits. Okay? We can calculate how fast the Earth moves in its orbit around the sun, how fast the moon orbits the Earth, okay? Things like that. All right, so let's see if we can figure out how fast the Earth is moving, or sorry, the moon is moving in its orbit around the Earth. Okay, so we're going to start out with this. Gravity is providing the centripetal force that holds the moon in orbit around the Earth. Okay, the formula for centripetal force is mv squared over r. And the formula for gravity is big G times m1 times m2 over r squared. Okay, so we're talking about the moon and the Earth. All right, so I need the mass of both the moon and the Earth. Agreed? Okay, they are both on your formula sheet. Okay, and so is the distance, the average Earth-Moon distance. It's under other useful constants on the back. Okay, the average Earth-Moon distance, 3.85 times 10 to the 8. Okay, all right, so that is the distance from the center of the moon to the center of the Earth. All right, so it would be r for this question. How many m's are in this question? 3. So let's figure this out. This is the mass of the Earth. This is the mass of the moon. What's this? What mass do I put there? Anytime we've dealt with circular motion, the object that's going in the circle ends up there, right? So which mass should go on the left side? The moon, yeah. The moon is the object doing all the circling, okay? The Earth is kind of the center. It's not perfectly it, but that's essentially what's going on. So this side here is always going to have the mass of the orbiting object. But now, I've got the mass of the moon on both sides. What's going to happen to it? It's going to cancel, right? So here's what that means. Mass of an orbiting object is irrelevant. Okay? It doesn't matter what I put out at the distance the moon is. I could put a basketball, a garbage truck, or the moon. They would all have to move at the same speed in order to stay in orbit at that distance. Mass is independent. Okay? It does not affect how fast you have to go. All that affects how fast you have to go is the radius and the mass of the object that is being orbited. Okay? All right, so let's calculate how fast the moon's got to move in its orbit. So we're going to look for V. So we're going to multiply both sides by R. All right, what's going to happen to the R and the R squared? They're going to cancel. All right, so I'm still going to have an R on the bottom, just not going to be squared anymore. Okay, and then as we said, the mass of the moon is going to cancel. So I'm going to have that V equals the square root of big G times the mass of the Earth, times or divided by the radius. That would be the distance between the moon and the Earth. Okay, so we got 6.67 times 10 to the minus 11 times the mass of the Earth, 5.98 times 10 to the 24 kilograms. Okay, divided by 3.85 times 10 to the 8 meters. All right, so the moon moves at about 1 kilometer per second as it orbits the Earth. Okay, that seems pretty fast, but when you're talking about how far the moon has to go in order to orbit the Earth, it's actually not all that fast. Okay, how long does it take the moon to orbit the Earth? What's that? Yeah, it's around 29 days, 28 point something days. Okay, that's how long it takes. So that's in fact why most cultures around the world developed a lunar calendar as opposed to a solar calendar. It was much easier to base your calendar on the movements of the moon because you could see it in its phases, as opposed to figure out where the Earth is in its orbit around the sun. Right? Okay, so we have 1.0 times 10 to the 3 meters per second. Okay, as our answer there. All right. Questions on how this gravitational stuff works? Everybody good with that? All right. So, as I was saying before, okay, gravity is important in the calculations involved in sending stuff off of the Earth. Okay, whether that's going to be making a Soyuz capsule rendezvous with the International Space Station, or sending a satellite into orbit, or sending something to the moon or to Mars or whatever. Okay, there's a lot of calculation stuff that goes into that, which means there's a lot of room for error. Okay, so what this diagram is showing you is all the missions that have been launched from Earth to other places. Okay, and there are a lot. Okay, we have sent a lot of stuff out into space. So the most visited object is the moon. Okay, we have sent more stuff to the moon than anywhere else. Now there's a color code to this. Okay, you can see that there are some bright colors, and then in between them are kind of these darker areas. Anywhere where you see a color and then its complementary dark area, the dark area represents a failed mission. Okay, so to the moon, we've had pretty good success. Okay, we get things to the moon fairly reliably. Look at Mars. There are a lot of dark lines. Okay, Mars has like a jinx. Okay, it's about 1 in 4. missions to Mars fail. Okay? Just stuff goes wrong. There's all kinds of things that can go wrong in the calculations and on the way there and whatever. Okay, reasonably successful to Venus. Okay, a lot of lines here that are bright. A few in the early going that didn't work. Most of the stuff that's gone to Venus is Russian. Okay? Back during the Cold War, they kind of said, well, the Americans got to Mars first, so we'll let them have it and we'll go to Venus. And they sent a bunch of probes to Venus, which oddly enough would have been far more challenging. Okay? Why would Venus be far more challenging? It's actually closer. Okay, closer to the sun, part of it. Yeah, not only melt, but crush. Okay, Venus's atmosphere is 100 times thicker than Earth's, 100 times heavier than Earth's. Okay, whereas Mars is the exact opposite. It's 1/100th of Earth's. Okay, so having things burn up in the atmosphere, not as much of a big deal. Landing things, okay, stuff like that, the atmosphere doesn't play as big a role. Okay, to land something on Venus, it has to be stronger than the deepest submarine, okay, can go on Earth, because the atmosphere on Venus is its crushing power, its weight is more than what you would feel at the deepest point in the ocean here. All right, so you have to build stuff that's very strong. And on top of that, it's hot enough to melt lead on the surface of Venus. So if you're going to land something there, it's not going to last very long, no matter how well it's built, right? So when the Russians sent stuff to Venus, their first couple, the first one was just an orbiter, that was successful. Okay, their second orbiter wasn't, and then they sent their first one. They wanted to just see how far down the atmosphere they could get it. Didn't get very far, and it crushed it like a can. Okay, just the atmosphere was so thick. So they had a lot of failures, which would not have been good if you were in Russian space program. Okay, you end up in Siberian salt mine for failure. Okay, it was not a good time to be in the Russian space program. So they had a bunch of ones that got crushed. Then they finally got one to land on the surface, and it essentially died within minutes of being there. So they sent another one. They just improved every single time. This one had a camera and a sampling arm. So they were going to land it, and then they were going to pop the lens cap off the camera, take some pictures, and then the sampling arm was going to touch the surface and take some readings. So they have the thing descend, it lands successfully on the surface, pops the lens cap off, and the sampling arm comes down and samples the lens cap. The only thing brought to Venus from Mars or from Earth is the only thing that gets sampled. That's why you don't put the camera right above the sampling arm. Major design flaw, right? The more you overtake the plumbing, the easier it is to stop up the drain. Okay, and so that's kind of what happened to these guys. But they did have a number of successful missions where they were able to overcome that problem with a slight offset of those two structures, so that they wouldn't interfere. But yeah, there's been lots of successful missions to Venus. We have a couple around Mercury at this time. Okay, but we don't have quite as many out here into the outer planets, because obviously it's a lot further to go. There's a lot more things that can go wrong. Okay, but we do have a lot of successful ones. Most of the ones that we've sent out to that distance have been successful. Okay, the failure element usually comes when you're trying to land on something. Okay, that becomes very difficult. There's a lot of unknowns that come in on that landing. The biggest problem with landing on another planet is trying to control the object from Earth, because there's a delay. Okay? Your signals can only travel at the speed of light, which means there can be sometimes 10 to 20 minute delay between you send a signal, it happens, a signal gets sent back to say, I did that. Okay, well, by then it's a smoking crater on the surface. Okay, so everything has to be built so that it can land itself, because it simply can't be done remotely from Earth. Okay, and when they landed the Curiosity rover on Mars, did anyone watch that? It was actually live streamed. For most people, it would have been really boring, but I'm a geek. So they were actually talking about how at one point it was either a smoking crater or it was successfully landed, but they weren't going to know for another 20 minutes. Okay, they just kind of set everything up, and then it was using a totally new landing system. Up until that point, everything landed with the airbags. Okay, so they would come down on a parachute, and then they would inflate these airbags, and the thing would bounce and roll along the surface and then come to a stop, and they'd deflate the airbags and everything would open up. But Curiosity was way bigger. It was way too big to land that way. So they had this, what they call the sky crane. a ring of rocket engines with the lander in the middle, and then a crane that would lower the lander from the sky crane, okay, down to the surface. So this was all done by the computer on board, not by any remote control from Earth. So they were very concerned about how it was going to work. So they got it to the landing point. The sky crane was keeping itself level. They lowered the Curiosity rover and dropped it the last, I think it was like 10 meters. That seems like a lot. But remember, it's on Mars. It's only like falling 3 meters. The Earth, Mars' gravity is 1/3. So they dropped it that far and then disconnected the cable, and the sky crane just flies off and crashes, which is what it was designed to do. Okay? Why wouldn't you just land the whole thing together? Yeah, well, yeah, the rockets would have destroyed the lander itself, right? And they'd have blown around a bunch of rocks that could have also damaged it. So they were better off to lower it slowly and then drop it and let the rockets just crash somewhere else where they wouldn't hurt it. So yeah, all kinds of interesting ways to get things like that to happen. But without the universal law of gravitation, we wouldn't be able to calculate how fast things would be going, what course to set, how much is something going to alter something else. And that's really important for all these outer solar system missions because they used what's called the Gravity Slingshot. Okay, you can't pack enough fuel on board a probe, okay, to kind of thrust itself all the way out there. What they do is they get it to come in next to one of the big planets and let the big planet's gravity accelerate the probe, okay, get it going really fast and then shoot off in another direction, okay, and so that's what they call the Gravity Slingshot. Right, just to alter its trajectory a little bit so it's not coming in. I mean, if it goes in and comes right back out on the same trajectory, it doesn't gain anything, right? So it comes in, it gets accelerated, and then goes off at a slightly different trajectory, having sped up. And they gain a lot of velocity that way, and that's how they get out to those far areas, by using what's called the Gravity Slingshot. You couldn't do that, again, without this formula that we've been looking at. Okay. All right, we did that problem already. Okay, I want you guys to try these two questions here. They have to do with the formula we were just working on. Okay, see how you do.